Hello, everyone. Welcome back to my Factoring Quadratics series. This will be the last lesson on that series. This is sort of just the bag of goodies that I haven't gotten to yet. I'm referring to these as the special forms. So these are the forms of quadratics you can see that don't necessarily follow the normal factoring rules, or you could factor them the normal way that I showed you in the previous lesson, but there are some shortcuts to these particular forms. So the first thing I want to get to is what's known as the difference of cubes. So apologize for my handwriting here. Let's see if I can make a prettier looking B. It's a little bit better, but still not great. Anyway, in this case, A and B can be anything. So most of the time we see, X in one place and a number in the other place. But all this is saying is I have a thing that I have squared, and I'm subtracting it by another thing that I have seen squared. One thing I want to point out is that this is not the same thing as saying I take A minus B. I just cannot write the letter B and I square it, right? These two things are not equal. The left-hand side here, I would have to FOIL out and it would end up being something a little bit different. It's just, I think a lot of you probably understand this already, but I see this mistake enough times that I wanted to point it out specifically. So if I have something squared minus something else squared, this factors really quickly and easily into A minus B and A plus B. So just the individual things that were squared. Oh, I apologize. A minus B, A plus B, not A plus B, A plus B. So one negative, one positive. So just as an example, let's say I have x squared minus 4. So my a squared term is x squared. My b squared term is 4. The key to these problems is identifying the thing that was squared. So I can very clearly see that x was squared, and I can very clearly see that 2 was squared. So 2 squared gives me 4. X squared is x squared. Because of that, I can go ahead and factor this down into x minus 2 and x plus 2. Now, we can do this with things that don't actually look nice squared if we really, really wanted to. I could realistically say that this is x minus the square root of 2 and x plus the square root of 2. Square root. It's not pretty, but technically it is correct. Generally speaking, your teachers will likely not give you that sort of thing on a test or a quiz. They will make sure that the factored pieces look nice. Maybe they'll have fractions, but they probably won't have decimals, and they probably won't be square roots. If you end up with that kind of question, that's more likely a question that you're expected to solve via the quadratic formula, which I have not shown you in this series, but potentially you already know, or potentially you have coming up. Another thing I would like to show you is that you could have a case where you have this sort of several layered difference of squares question. So let's say, for example, I have x to the 4th minus 16. Well, I can identify here that the thing was that was squared was x squared. So x squared squared gives me x to the 4th. And over here, the thing that was squared was 4. So I know that this should factor out into x squared minus 4 times x squared plus 4. However, if I look closely, I notice that one piece of this looks like another difference of squares, which it is. So I can go even further. I can say, well, x squared minus 4 should give me x minus 2, x plus 2. And you're probably asking yourself, well, Eric, what about the other piece? Can I do anything with the other piece? No, you can't. Not without what are known as complex numbers, or oftentimes called imaginary numbers. So this is very important. The sum of cubes, or I'm sorry, the difference of cubes always factors. The sum of cubes never factors. Or did I say cubes? I meant squares. I apologize. So difference of squares factors, yes, always. Sum of squares never factors. Without, waving our math magic wands around. Let's do something a little more difficult, just to illustrate a point. So I'm going to say 4x squared minus 9. So this is the difference of squares. I need to, once again, identify in each case the thing that was squared. 9 pretty clearly is just 3 squared. 4x squared, we should be able to identify as 2x. So notice that both the coefficient in front and the variable itself were squared in order to get this. And that's important. Otherwise, it would not be a proper difference of squares. But here I can go ahead and say that I have 2x minus 3 and then 2x plus 3. So that can also happen as well, where your pieces are a little more complex than just a variable or a number. It could potentially be both. You could have a situation where you have each piece has a, let's just do like the same thing as last time. Each piece has its own variable. So here I have one piece having x's, one piece having y's. I can still do the same thing where I identify the thing that was squared. And then I just say, oh, it's plus and minus those two things. So I have 2x minus 3y, 2x plus 3y. In addition, let's recall one of our golden rules of factoring. And that is that we should always identify common factors and factor them out first before we apply any of these other factoring rules. So for example, I look at this and I say, well, each of these two terms has a y in it. So I can factor a y out and be left with 4x squared minus 9y squared. And then I can look at this piece and say, hey, that's a difference of squares. But I had to previously factor out any common factors that I saw. And that can be true of, having extra variable common factors. You could instead have extra numerical factors. So let's see if I can come up with these numbers on the spot. Let's see, 16x squared, and then I believe 36y squared. I would say, hey, these both have a common factor of 4. And then from there, I can take this piece once again and say, that is the difference of squares, and factor that. So that's pretty much all I have to say on the difference of squares. Let's remember that the difference is important. The fact that it's a negative sign allows you to factor, whereas if it was a plus sign, you could not factor. I do briefly want to touch on the sum or difference of cubes. So if instead of a squared minus b squared, what if I had a cubed minus b cubed? What does that factor into? What does that look like? Now, technically, this is not a quadratic, but this is commonly taught in this kind of section, in this unit of math. So if I'm going to go through the motions of teaching you all the ways to factor quadratics, it feels like it would be incomplete without kind of going over this. So if you haven't seen this yet, chances are you're going to see this soon. So pay attention. The sum or difference of cubes, yes, that's right. They both factor, both the sum and difference of cubes factors, whereas the sum of squares does not, but the difference of squares does, right? So for squares, only one of them works. For cubes, they both work. This factors into, and this is going to look weird at first, but I'm going to go ahead and explain this all down the line. Don't worry about it. Oh, you know what? I should probably keep consistent with if they're all capitalized or all lowercase. And I made a small mistake here. Okay. What do these all mean? I have this situation going on where I said plus minus, and then the other one is minus plus. What is that saying? So notice that here I have wrote plus minus. So in this first little binomial term, the plus minus is indicating that it is the same sign as the original unfactored version. Notice that the second one, it's instead of plus minus, it's flipped. So this is this is letting us know that this is the opposite sign. And then this one is just always positive, so you don't have to worry about that. So if you have something cubed plus or minus something else cubed, it factors into the first thing, a, not the cube, just a itself, plus or minus b, times a squared, not a cube, but a squared, the opposite sign, and then ab multiplied together plus b squared. We have a fancy name for this because we have the same side, or I'm sorry, same sign, opposite sign, and then this is always positive. If I could spell always. Okay. We have same sign, opposite sign, always positive. So we call this SOAP as the little acronym to help us remember. So SOAP refers to same, opposite, always positive for the signs. Unfortunately, you still do need to memorize what goes where. Is it an A or is it an A squared? Do I multiply the two together here? You'll have to remember those things. So let's see here. Let's go ahead and once again, make an example. So I'll just go with the classic. Let's say x to the third power plus 27. So now what I'm looking for is I'm looking for what did I cube, not what did I square, what did I cube to end up here? Well, the first term, it's just x. I just cubed x. 27 is 3 times 3 times 3. And then also here I have to know which sign because that's going to affect my final answer. So I should have a plus 3, or I'm sorry, a plus b, which is x plus 3. So notice I didn't raise them to any powers. The next term, a squared, so it has to be x squared. Let's see, the opposite sign, and then a times b. So 3x, x3, 3x, they mean the same thing. And then always positive, and then b squared. So 3 squared, which is 9. So this is a nice little breakdown of the sum or difference of cubes. All the same rules I just went over for the sum of difference of squares applies here. You could potentially have a situation where you're not just cubing a variable or a number, but some combination of both. So if I redo this example, but instead of just x cubed, it is 8x cubed. And you know what, since we're already going there anyway, let's just say plus 27y to the third, right? So each of them has a variable and a numerical piece. And I have to ask myself, well, what thing got squared? So for 8x cubed, 2x, oh, did I say squared? I meant cubed. I flipping those back and forth. So 2x was cubed to get 8x cubed. And then 3y was cubed to get 27y cubed, which leads me to the factored form 2x plus 3y times, remember, a squared is the first one, so that'll be 4x squared, 2 squared, and x squared. The opposite sign, and then a and b multiplied together, so 2x times 3y should give me 6xy, plus, because it's always positive, b squared. So 3y squared should end up with 9y. And there you go. There you have it. Remember that the sum or difference of cubes, both the sum and difference do work, as opposed to the difference of squares, which is only valid if it's the difference, only valid if it's negative. Get rid of all this. Maybe I'll write that just for clarity's sake. You guys probably by now notice that I cannot write the letter B. So one of these things does not work, but the rest all do. All right. So there is another situation that I want to talk about, and that's that's if we have this situation. If I have a binomial term that is squared, so in other words, I have two of the same binomial term, what does that end up looking like, and how can I factor it nicely? So usually the way I've been handling this is we go backwards, right? If I want to know how to factor a nice quadratic into this, I need to know first how I get from this into the quadratic. So I'm just going to expand this out. So if I'm squaring a binomial, if I'm squaring anything, it just means I have two of them multiplied together. And I'm going to go ahead and FOIL this. So I have a squared plus ab plus ab. You could write the other one as ba, but I'm trying to keep them similar so I can recognize that these two are like terms. And then plus b squared. Okay. And then if I just add my like terms together, I get a squared plus 2ab plus b squared. All right. So you'll notice that this factors into something that looks like this. So let's just kind of observe. Let's take a look at this. Notice that the first and last term are just perfect squares. So if I run into a quadratic and I see I have a perfect square on one end and a perfect square on the other end, I might have this scenario. This might be going on. And it's just up to me to figure out, is the middle term actually 2ab? So for example, let's take a look. I got to come up with something on the top of my head. Let's say 4x squared plus 3 And then the middle term would have to be 24x. Okay. Oh, I'm sorry. I already messed this up. The last term needs to be 9. All right. So I notice that the first and last term are in fact perfect squares, right? One is 2x squared, and the other is 3 squared. So the question is this thing equal to 2 times 2x times 3? And no, it's not, because I messed up this problem. Excuse me. 12. All right. You didn't see anything. So 2 times 2x is 4x times 3 is 12x. Hey, would you look at that? It's perfect. Who would have guessed? Who would have thought? So I notice then that this thing here, this quadratic, fits the proper form where the two ends are squared, and then the middle term is 2 times the first, like, you know, the square root of the first term and the square root of the second term. So the thing that was squared in each case came together and was multiplied by 2 to get the middle piece. So I can then say, because I identify the things that were squared, right? I identified it was 2x and I identified it was 3. So based on what I have found here, you know, kind of snooping through all of the evidence, is that this must be 2x plus 3 squared. So I do want to say that these signs here, these positive signs in my original sort of like generalized example, in order for this to work, this one does always have to be positive. And that's because if I square something, it has to be positive, right? So even if b was a negative number or a negative term, it's b times b, which is going to end up being positive no matter what. However, this could be plus or minus. That middle term could be either of the two. And that would indicate to you which way A or B goes. Is it positive or is it negative? We usually, for the sake of simplicity, say that B is the one that's negative, because putting a negative sign in front of your A term just looks ugly. But let's go ahead and, you know, let's re-look at this problem. Let's do this problem again. And let's just suppose that it had a negative sign in the middle term instead of a positive sign. What does that say? Well, I still know that 2x was the thing that was squared. Here I know that 3 is the thing that's squared, but I do have some sort of indication that the thing that was squared was actually negative 3, not positive 3. And if I look through this once again, if it's 2ab, it's 2 times 2x times negative 3, which lo and behold is negative 12x. So this gives us the information that our factored form is now, instead of 2x plus 3 squared, is 2x minus 3 squared. And that's it. So remember that for these guys, these are like your perfect square trinomial terms. Your middle term could potentially be negative, but your last term always has positive in order for this to work. So just as a little bit of a review, if I have a quadratic and I notice that the two terms on the front and the back are both perfect squares, I potentially have this situation. And I just have to check if the middle term fits the bill in order to kind of shortcut this out. Once again, you can do this the normal factoring way, right? Like I can take 4x squared minus 12x plus 9, and I can say, okay, What are two numbers that multiply to be positive 36, but add to be negative 12? I can still do that. Oh, it's got to be negative 6 times negative 6, and then negative 6 plus negative 6. Hey, would you look at that? I found my two numbers. I can split the middle term. I can do all that stuff like I had done before. You're not trapped to only using this special form and memorizing and making sure that you can identify it every time. You can still fall back on the other stuff. It's just, if you practice this, you'll notice that this is much faster than doing things the other way. All right. The last thing I want to discuss is something called quadratic in form. So we know that, generally speaking, oh my God, I don't want to talk about it. Generally speaking, a quadratic looks like this. This is the standard form for a quadratic expression. I have it ax squared plus bx plus c. What is important here, what I want to point out, is the powers of x. One is squared, one is to the first power, and then c, you could, if you wanted to, you could say this is x to the 0th power. We'll go ahead and just say no x. There's no x here, right? These do not have to be exactly this way. Your variable just needs to be squared here, be not squared here, and be completely absent here. So the following is quadratic in form. 2x plus 4 square root of x minus 7. That doesn't look quadratic, does it? However, I can definitely say that x is just the same thing as the square root of x squared. Some people are probably yelling at me about that regarding what happens to the plus or minus, blah, blah, blah. Let's not worry about it. That's for a different time, for much later. So I can look at this and I can say, well, I have a form of my variable that is squared in the first and then is by itself in the second, in the middle term, and then is absent in the last term. So I can still factor this like I would a quadratic expression. You know, I can still go through all of the hoops. It's just my two terms at the very end will be the square root of x, I don't know, minus, I'm just making stuff up, 7 square root of x, or 2 square root of x plus 1, whatever. I don't know what it actually factors into, but you get the idea. I'm factoring into, instead of x plus or minus something, into square root of x plus or minus something. So the sky is the limit with this. Let's say I have x, 1 over x squared plus 3 over x plus 4. This is quadratic in one way or another. I have a thing which has been squared plus, I'm going to go ahead and write the 3 out in front. That thing plus a constant term with none of that thing in sight. So I could still factor this as a quadratic, and you guessed it, it will factor into some ugly stuff, which is going to be like 1 over x plus a number, 2 plus or minus. Oh, you know what? Actually, this one does factor, does it? No, it doesn't. Never mind. But it's close. Well, you get the idea. So pretty much everything stays the same. It's just what you end up putting in place of x that changes. I will say that this is not likely to be something that you run into if you are in your first year of algebra. If you're in algebra 1, I wouldn't worry too much about this stuff. it's probably not going to come up. If you're in Algebra 2 or if you're in pre-calculus, this will probably come up. And for those of you who are going into, engineering or physics or some other physical science, yeah, you do see quadratic in form, fairly often. For those of you who are here just for the review, you might end up seeing something like this, right? How many times have you seen something like this? This is very common, right? Okay, you don't even have to, for those of you who have never seen this, you don't even have to know what it is. All you need to know is I have a thing, it's squared here, and then it's not squared over here. So I can factor it. Even if you have never seen this thing that's called sine theta in your life, you can at least look at it and say, well, I can factor this, I guess. So be on the lookout for those things. But really, I just gave it to you here just to be as thorough as I can be. I want to make sure that I give you guys as much information that hopefully is relevant that I can. But the truth is, this quadratic and form stuff, this is the very last thing I'm showing you for a reason. So hopefully everything that I have shown you up to this point has been clear. Feel free to comment on things you think I could do better. I know that equipment and hardware will probably come up. Unfortunately, that's not something I can solve at the moment, but anything else about presentation, I would love to hear what you guys have to say. And I, once again, hope this has been helpful for you, and I will see you hopefully in another one of my series. Bye.